Hello and welcome to this quick review of moles, solutions and titrations. As always, the clip should be used after you've done your independent study, and this time we'll also assume that you've already covered the basics of the mole concept. So let's start with the idea of concentration and dilution. So the concentration of a solution is measured as the amount of solute in moles dissolved per 1 decimeter cubed or 1000 centimeters cubed of solvent. So it's calculated by working out the number of moles of solute present, and it's written in moles, MOL for short, by the volume of solvent in decimeters cubed in which it's dissolved. So if you take an empty container, a beaker or volumetric flask, it doesn't really matter what the container is, but assume it's got a volume of 1.0 decimeters cubed. You now fill it with solvent, make the solvent water, for example, and if you add a mass of solute equivalent to 1 mole, for example 159.6 grams of copper sulfate, assuming that all the sample of copper sulfate dissolves, you now have a concentration of 1.0 mole per decimeter to the minus 3. So we can work out moles in solution very easily using the equation N equals V times C, where N represents the moles of solute, C equals concentration in moles per decimeter to the minus 3, and V equals volume in decimeters cubed. However, what happens if in your question or in your titration or in your workings you're given the volume in centimeters cubed, not decimeters cubed? So the standard unit of concentration is always moles per decimeter to the minus 3. So if we get our volume in centimeters cubed, we need to convert it to decimeters cubed by dividing centimeters cubed by 1000. So if our volume is in centimeters cubed, we simply use N equals V over 1000 times C instead. And as you'd expect, there are some rearrangements that you may have to use. Concentration is moles over volume, and volume is moles over concentration. So you're remembering the units as moles in MOL, volume in dm cubed or decimeters cubed, concentration in moles per decimeter to the minus 3. So the solution becomes more dilute excuse me, if more solvent is added to the same moles of solute. So if you look at the solutions in the diagram, they all have the same moles of solute, 1 mole, but different concentrations. The reason for this is going from left to right, we have added more solvent each time, so there's less moles of solute present per decimeter cubed of solvent. And we can use N equals C times V to mathematically prove this. So let's now have a look at the application of this idea. The most common application you'll come across in chemistry is by far the titration. So a titration is a chemical procedure where we take a solution of known concentration and we react it with another solution of unknown concentration. So we'll know the mole ratios in which the two solutions react. So if we take a typical example, the most common one that we use at GCSE and at A level to illustrate this is sodium hydroxide and hydrochloric acid. You can clearly see from the equation that there's a 1-to-1 mole ratio. So this would mean we'd expect equal amounts of moles of NaOH to react with HCl in this reaction. So first you set up a retort stand. And the next thing to do is to attach a burette to the clamp. So the next thing to do is to make sure the burette is positioned so a conical flask can sit easily on the base of the retort stand, yet still be directly below the burette. And as you can clearly see, in this case we need to move the burette closer to the retort stand. So you place a white tile on the base of the retort stand. The white tile allows you to see what's happening, a white background against which you can see colour changes. And a fixed volume of a solution of unknown concentration is put into a conical flask. So the solution, we know what it is. It'll be one of the two reactants that we've got in our equation, but we won't know its concentration. So we then fill the burette with our standard solution. It'll be our other reactant, so known identity and known concentration. So now we have our two reactants ready to titrate. So before we begin, we need to add a few drops of indicator to the unknown solution. We need to swirl this to mix it. You then start to add the standard solution from the burette until the indicator starts to change colour. Now you stop adding at this point. Now you can start adding again, but very carefully, dropwise, making sure you swirl constantly and you stop when the colour change is permanent. So the volume of standard solution you've added is called a titer. So this particular titer won't be very accurate because it's the first one that you'll have done. So we therefore call it a trial titer or a rough titer. So the titration procedure is then repeated with fresh samples of unknown concentration solution, that is in the conical flask, until two titers are within 0.1 cm³ of each other. These are called concordant titers and are averaged then to arrive at an average titer. So we'd normally lay our titrations out in a table like this, with the initial, final and then the worked out titer. There's a few points I need to make at this stage. You don't have to start at 0 each time, but it just makes working it out a little bit easier if you knew you started at 0 cm³. All your data must be to 2 decimal places, and never use a trial titer to work out your average titer, even if it seems concordant with another reading. So let's get to work with this data and see what we can do with it. So we can start by saying titers 1 and 2 are concordant. So if you average those two values, titers 1 and 2, that gives you 24.05 cm³. So coming back to our burette and our conical flask, the volume we usually use is 25 cm³ in the conical flask for convenience. So in the burette, we know that 24.05 cm³ reacted fully with 25 cm³ of your unknown solution. So let's assume our standard solution was 0.5 moles per decimeter to the -3 NaOH. So the number of moles of NaOH reacted is V over 1000 times C, which gives us 0.0120 moles. Notice I'm writing it out in 3 significant figures. And coming back to the mole ratio of the sodium hydroxide and HCl in the equation, we can now say that the number of moles of HCl reacted is also 0.0120 moles. So the concentration of the HCl is N over V, which is 0.0120 over 25 over 1000, not forgetting to convert the units, which gives us 0.481 moles per decimeter to the -3. So just to sum up, titrations are used to work out the moles and concentrations of unknown solutions using known reactions they take part in. And at A level, they're commonly applied to acid-base neutralization reactions to calculate the concentration of one of the reactants. Okay, so hopefully you found this a reasonably useful introduction to the titration technique and how we use mole calculations to support it. So thanks for your time, and until next time, see you soon.